our friends from Texas A&M. Ben Rogers, I think, is going to give the main part of the presentation, but Dr. Banerjee is here as well to answer any questions. And so this is on the carbon footprint of our battery versus lithium ion and other technologies. So Ben, take it away.
Well, thank you so much for having us today. My name is Ben Rogers, and I have the honor of studying under Professor Sarbajit Banerjee here at Texas A&M University, as well as working with Professor Manish Dixit here at Texas A&M. So if we move to the next slide, I want to frame vanadium as why do we consider it the green metal and how are we looking at it? And we want to look at it through the lens of enabling the energy transition to make truly deep transformative decarbonization hinging on strategic minerals. And the versatility of vanadium chemistries enables many technologies such as vanadium flow batteries that can lower carbon dioxide emissions overall. And the way we are viewing vanadium is through benchmark assessments in which can be applied to all critical minerals to inform the design of public policy for balancing and expanding critical materials access. So moving to the next slide. We've done some previous research in the vanadium consumption and different industries, and we've looked at different use cases such as rebar, steel sections, automotive steel, and vanadium flow batteries to quantify the benefits of vanadium through both carbon and energy savings resulting from incorporating vanadium into these value-added products. So moving on to the next slide, I want to highlight some previous research that we've done here at Texas A&M University, which is great further reading for how we perform these benchmarked assessments, and basically just highlight a few papers, including one that we're working in progress, which is covering the vanadium supply chain. So going on to the next slide, we see pretty consistently across decades is that it's really the building materials embodied energy cost that makes up by far the largest percent share of the energy consumption in overall construction, and not the construction process itself. And so when we look at savings from the carbon footprint and embodied energy costs, we see that the biggest contribution in reducing the carbon footprint and embodied energy will come from the building materials and embodied energy to have the biggest impact overall. And so here at Texas A&M, we've developed a life cycle assessment framework with 4 key steps: modeling, material savings, a life cycle inventory, and an impact assessment in order to make these quantitative assessments. And so going a little bit deeper into the next slide, in the modeling and material savings phase, we can look at individual components to calculate the material savings. And so for both section steel and in a use case, such as in a building, what we found was that there is a 61.06% savings in steel from a 500 megapascal steel and reinforced concrete beams over a 250 megapascal steel. And thus the savings in structural steel can translate into reduced carbon emissions in a use case. And so going on to the next slide, we were able to scale this up to a global scale as well. And so what we found was across the world, by incorporating vanadium microalloying, we found that there was a 136 megatons of CO2 emissions reduced, which is 0.38% of global carbon dioxide emissions. But also we can look at different regions and countries. So in China, we found that through vanadium microalloying, that there was a 100 megatons of CO2 emissions that could be reduced, equivalent to 1.01% of the nation's overall emissions, as well as looking at different regions such as the European Union. So we found that there was, through vanadium microalloying, 6.6 megatons of CO2 that could be eliminated as well, reducing the carbon footprint across multiple scales. And so taking it back to our life cycle assessment framework, in our life cycle inventory stage, we can calculate the materials impact through the embodied energy costs and the embodied carbon dioxide costs. And then what we did was we wanted to break it down to the different use cases, so section steel and rebar steel, and then apply that in the different regions of interest. So the European Union, 28, China, and then the world at large. And this allows us to do a
Now,
better.
I understand that ultimately, some
Sorry, if
quantity
you
of
go back and then,
Yeah.
yeah,
Sorry. There we go.
I guess this, yeah. And then if you go forward again, it should hopefully cut out the audio.
Now, I
Uh,
understand that
maybe
ultimately,
forward and backward.
some
That's
quantity
okay.
of CO2.
But overall, what we wanted to do was look at how the reduced energy costs, thus translating to reduced carbon emissions, can scale overall, which is worldwide equivalent to 30 million passenger cars driven for an entire year and 300 million barrels of oil consumed just by incorporating vanadium as a microalloying additive. And then this can also translate to carbon dioxide savings, such as 30,000 wind turbines running for a year or 40 million tons of waste recycled instead of landfilled. And so when we look at the energy landscape overall, what we see is that vanadium flow batteries, which have an optimal, generally operate on the intraday to multi-day scale or duration period, we see that energy storage overall has a lot of different time spans, but for vanadium flow batteries, focusing in this area in particular, we can do a comparison of the different use cases and carbon emissions reductions by using vanadium flow batteries. So going to the next slide. There are two key aspects of the vanadium flow battery life cycle assessment framework that I want to highlight. The first is curtailment. And this is basically asking the question, are the net savings from installing a vanadium flow battery still positive after accounting for its carbon footprint? And then we also wanted to ask about the performance compared to lithium ion battery technology, and which has the smaller carbon footprint. And by doing our life cycle assessment framework, we're able to make these comparisons. So going on to the next slide. This is some of the research that we've done here at Texas A&M. So using some previous calculations from a previous life cycle assessment framework, what we found was that for vanadium flow batteries under the current operating conditions and performance specifications, we see that vanadium flow batteries outperform lithium ion batteries when coupled to renewable energy sources. And so when you have a lower carbon intensity electricity generation source, we see that the overall carbon footprint of vanadium flow batteries outperforms. But when you have a higher carbon intensity of electricity generation source, the carbon footprint for vanadium flow batteries is higher than lithium ion batteries. So going to the next slide. We need to make some key specifications in order to make these comparisons effectively. And so some of the points are looking at the charge-discharge efficiencies of vanadium flow batteries versus lithium ion batteries, in which we consider generally vanadium flow batteries have a operating efficiency right now at about 70 to 80%. So looking at 75%, and then for lithium ion batteries at 90%. And then we also consider the environmental impacts, the recycling, so the different production stages of the battery and end-of-life handling, as well as quantifying the benefits from cradle-to-gate impacts of the battery systems. And so when we consider the recycling scenario, what we see with vanadium flow batteries is that there is already an inherent advantage in the manufacturing process at having a reduced carbon footprint. So for vanadium flow batteries, in comparison to lithium ion batteries, there's 17 kilograms of CO2 per megawatt hour, smaller carbon footprint than lithium ion batteries, even before considering any recycling processes. But then once we consider recycling and the cradle-to-gate impacts of the battery manufacturing, we see that the advantage grows significantly higher from a 30% smaller carbon footprint to a 78% smaller carbon footprint. And that reduced carbon footprint advantage grows from 17 kilograms of CO2 per megawatt hour to 33 kilograms of CO2 per megawatt hour. And this can be attributed to the excellent recyclability of the vanadium electrolyte, creating more value at the end of the vanadium flow battery life cycle. So going on to the next slide, we see that across the whole life cycle, we can look deeper using our life cycle assessment framework to make quantitative comparisons between vanadium flow batteries and lithium-ion batteries and their carbon footprint of generation as well, energy generation, or energy storage rather. So for vanadium flow batteries, when coupled to a wind source, we see the biggest reduction in the carbon footprint compared to lithium-ion batteries at 30.6 kilograms of CO2 per megawatt hour. And for photovoltaics, we still see an advantage, albeit somewhat smaller, at 9.8 kilograms of CO2 per megawatt hour. And then when compared using a mixed grid energy generation source, we see that the energy storage of lithium-ion batteries has a smaller carbon footprint under current efficiencies. And this is because of the inefficiencies of carbon-intensive sources being amplified when coupled to vanadium flow batteries under the current energy storage efficiency specifications. And so going on to the next slide, what we found was that if coupled to a wind source, vanadium flow batteries are projected to save 2.13 million metric tons of carbon dioxide across their 20-year lifetime, which is roughly equivalent to 2.6 million acres of US forests in 1 year. And the advantage of vanadium flow batteries, having a smaller carbon footprint, performs the best when coupled to energy generation sources that have a lower carbon footprint to begin with, such as wind or solar. And so when we look at the projected operational capacity of vanadium flow batteries overall, we can consider that under the different use cases of vanadium, such as the recycling profile of the vanadium flow battery and the round-trip efficiency, that overall these factors play a significant role in determining the carbon footprint of the vanadium flow battery. And then what we did was we looked at the curtailments and the comparative assessment with the lithium-ion battery. And we found that the curtailment savings could be maximized as innovation improves vanadium flow batteries. And so on the next slide, we can see that once we consider the advantage of recycling vanadium flow batteries, and as increased efficiencies in vanadium flow batteries grow, what we see is that across all electricity generation sources, solar, wind, and a traditional grid mix, that the carbon footprint of vanadium flow batteries can indeed outperform lithium-ion batteries across all power generation sources. And here on this graph, we've showing the most important line, I would say, is with the increased efficiencies, is the bottom orange line outperforming lithium-ion batteries across all carbon intensities of electricity generation from 0 to 1,000 kilograms of CO2 per megawatt hour. And on the next slide, we can compare and look in context of the Guidehouse Insights predictions. And so they did a country by country or region by region breakdown. And when looking at the different power generation sources, we see that the curtailment in terms of million metric tons of CO2 is greater when coupled to wind rather than wind and solar, which follows our previous conclusions that the smaller carbon footprint electricity generating sources have amplified the advantage of using vanadium flow batteries to reduce carbon footprint. And then this can also be used in the comparative assessment as well, in which we found that the carbon savings are also better for wind over the wind and solar power generation grid mix. And vanadium flow batteries are continuously improving. And so what we wanted to do was consider the different scenarios where energy efficiency from the 70 to 80% range right now to over 90% as it improves, comparing to the over 90% efficiency for lithium-ion batteries. And then energy efficiency of vanadium flow batteries, as well as electrolyte concentration, are going to improve vanadium flow battery performance and reducing carbon footprint. And then electrolyte conductivity as well to decrease internal resistance. And so the utilization of electrolyte in vanadium flow batteries right now is currently at about 60%, but that's going to improve over time as well. And thus we'll see that vanadium flow batteries will continue to improve their efficiencies and amplify their advantage in carbon footprint over traditional lithium-ion batteries. And so looking at the perspective of a global scale, there's in the preceding steps to the value-added product for vanadium flow battery production, we see that we're also we see that across the supply chain, the production is primarily concentrated in, no surprise, South Africa, Russia, China, and Brazil, but that there are significant global distribution of deposits across other countries as well, such as in North America and Australia, that are under development but not actively producing. And you can see this on the Vanatech website, where it's a beautiful visual illustration of the different production facilities, processing facilities, and vanadium flow batteries. And we're continuously updating this with new information, which my email can be reached at here on the slide. And so we can go to the next slide. And we're also working on an interactive carbon calculator where we want to quantify the carbon dioxide emissions for different vanadium value-added products, such as vanadium oxide, pentoxide flake, ferrovanadium, and in slag byproduction as well. And as within our previous research, we want to take in a diverse range of factors, such as geographical location, grid mix, and transport type, to quantify the CO2 emissions for the different value-added vanadium products. And going to the next slide. Of course, we're always incorporating feedback, so my email again. And then in current knowledge, for vanadium manufacturing, the CO2 emissions of vanadium production are calculated by a large range. And what we really see is that there's pretty significant disagreement across a range of sources, but this could be due to a lot of reasons, such as different calculation methods, different production methods. And so what we want to do is take into account all of the different production steps in a transparent way so that we can make a quantitative comparison between and account for the different production routes of vanadium. And so going on to the next slide, the need for a clear accounting of vanadium and carbon energy costs. Looking at the primary production route first, an overview, we see that the blast furnace and the electric arc furnace routes are both quite energy intensive and emit a high amount of CO2 emissions, which is why it's traditionally considered a hard to abate sector. But in the secondary production routes, we see that the steps for producing V2O5 from industrial fly ash and spent catalysts are significantly less energy intensive on an overview level. And so what we want to do is quantify the energy of each of these steps and really to identify the exact energy demands through producing V2O5 in each of these routes. And so it's very important to have a clear accounting to benchmark these process improvements over time. And then what we can do is use these pieces of information to compare vanadium flow battery technologies to other alternatives. And then also incorporate this in our carbon calculator to provide transparent, trustable, evidence-based values to all stakeholders. And again, my email's at the bottom if you have any feedback about the different process steps I may have missed or think are important to highlight. And some key conclusions I want to highlight for today's presentation are that vanadium flow batteries are critical to avoiding curtailment of solar and wind energy production. And what we see in vanadium flow batteries is that there is an advantage in the manufacturing process over lithium-ion batteries And on the slide here, I actually have the recycling numbers, but this is the energy advantage when coupled to a wind and solar source over lithium-ion batteries. And as well as the carbon savings and the enhancements of round-trip efficiency, reducing carbon costs of vanadium production, and improvements in recycling both of electrolyte and the stack components. And then we're also tracking the vanadium flow battery installations and vanadium production and processing worldwide in our World of Vanadium Living databases. And then we're also having in the works a carbon calculator for the entire workflow of vanadium extraction to battery use case. So thank you so much.
Great. Thank you so much, Ben. A lot of information there, but very exciting news for us. I didn't see any questions for you